momentum and impulse. Talking about momentum, for you to say that a body has a momentum, that particular body must have mass and it must be moving. If there is no mass, you can never have what we call momentum. Some people will tell you you've been gathering momentum. Some will tell you the momentum of a spirit. I don't know. But if there is no mass, there is no momentum. Now, this and this, they talk about the same thing but from different perspectives. These talk about a matter or a body with its character of what it's doing and how it's doing it. While this one talks about the same body or matter with what is causing it. We're looking into that now. Momentum, which we can define as the product of mass and its velocity. Momentum, conventionally represented as P, is equal to mass times velocity. That is the mathematical definition of momentum. While impulse is the product, it is conventionally represented as I, and is the product of force applied and time of its application. That is force times time. Now, momentum is discussing velocity, how the body moves. While impulse is discussing the force, which means what caused the body to move. Just like in force, we have in motion, we have kinematics and we have dynamics. Kinematics discusses how the body is moving, while dynamics discusses what causes the body to move. So here now, momentum is a kind of kinematic, while impulse is a kind of dynamic. It creates or check the character of how that body is moving. That is why it's studying velocity. While impulse is studying force, which means what caused that body to move. But now we'll see or relate how both of them are the same. Because we have to prove that impulse is change in momentum. And once we achieve that, we can now say that yes, they are saying the same thing, but it's just from different perception. If here we have force, we know that force is mass times acceleration, which is mass times A times T. And we know what acceleration is, which is change in velocity all over time. So we'll say that impulse is equal to m bracket change in velocity delta V over time times this time here. So time will marry time and both will go for honeymoon. So we have I equal to m delta V. That is mass times change in velocity. Bringing it down further, we have change in velocity is final velocity minus initial velocity. So we have m bracket v minus u. Opening up the bracket, impulse is equal to mv minus mu. And you know that momentum is mass times velocity. If we look here, we'll see mass times final velocity, and here we'll have mass times initial velocity. So we'll say that impulse is equal to P final minus P initial, which means that impulse is equal to change in momentum. And since they are the same, we can now say that truly both are talking about the same thing, but from different perception. I'm bringing down the units. This is mass times velocity. We have mass to be in kilogram, while velocity is in meter per second. Over here also, impulse, which is the same thing, change in velocity, is kilogram meter per second. But from here, which is talking about dynamics, we have this to be Newton, which is force, and time in seconds. So we have Newton second. Please beware of this. Not Newton per second, but Newton second. It's only per second when it's force over time. Many students in the exam is say which of the following correctly represents the unit of impulse. And the option A you will see is Newton per second. You see students will rush and shed that. It is not correct. The answer is Newton second. I'm bringing it to dimension. This cannot give us our dimension. We have to break it down further. So we can bring our dimension from here, kilogram meter per second, with kilogram now in dimension, which I handled earlier, will be on mass, while meter will be on length, and second will be on time, raised power minus 1. So this is the dimension of momentum and also dimension of impulse. In exam they may ask, which of the following has the same dimension as momentum? The answer is impulse. Now let's look at system of two colliding bodies. When you have two bodies coming together to collide, there are three possibilities that will come out as an outcome. First, if I have a body A coming this way and I have another body B coming this way, they are coming to have a collision. The principle of conservation of linear momentum states that in a system of an isolated system of two colliding bodies like A and B, that the momentum before impact, that is before they collide, must be equal to the momentum after impact. That means if I take this to be my before and coming over here to have after, I said that there are three possibilities we'll see after. It is possible that A and B will collide and there will be no movement, just like heavy blocks. This one will be coming and this one will be coming, they jam together and none of them will move. This is a possibility. The second one is that it is possible that maybe A is too big and B is too small, so that A will hit B and move in this direction, but this time both will move with a common velocity. Here A is coming with a velocity, let me say u1, and B is coming with a velocity u2, and it has this mass here m1, and here it has this mass m2. Coming over here now, the mass is still there but no velocity. That means there is no movement here, and since there is no movement, remember what you said initially, that when there is no velocity there is no linear momentum. But over here now, truly B was coming before, A was coming, but they collided, and because A is too big, it can push A, it can push B in its own direction with now a common velocity. It cannot be the velocity of A, neither will it be the velocity of B, because no matter how small B is, it will give a little reduction to the velocity of A. So but both are moving with the same velocity. We call it a common velocity V. This is also a possibility. We may also have a possibility where A and B will jam themselves or collide and move back to the position where they are coming from, such that here we'll have A going back this way with a velocity v1, which is the final velocity, and B going back this way with a velocity v2. Their masses are still there. The mass will not change because of collision. And they said that the momentum before collision, that is here, must be equal to the momentum after collision. Now, taking the momentum before collision, we take here the momentum of A, which is m1u1. We have that m1u1 plus the momentum of B, which is m2u2, and this is what we have before collision, m1u1 plus m2u2. Now after collision, here we have the momentum to be 0. Why? Because no movement, even though the masses are there, but there is no velocity, so it's 0. Coming over here, we have m1, which is the mass of A, and m2, which is the mass of B, all now moving with a common velocity v. And over here we have this one, we have m1 v1 plus m2 v2. Now if we obey the rule that says that the momentum before impact must be equal to the momentum after impact, that means that for the first case here, what we have is m1 u1 plus m2 u2 equal to 0 for the first case, because the one before must be equal to the one after. For the second case, we have m1 u1 plus m2 u2 equal to what we have here, which is m1 plus m2 all bracket v. For the third case, the same, m1u1 plus m2u2 equal to the one after collision, which is m1v1 plus m2v2. These three equations are very important whenever we talk about system of two colliding bodies. Most especially these two for any exam. Watch out for it. Call it UTME, call it WAEC. Look out for these two equations. This one, the two bodies are moving with common velocity after impact, while here each one is moving with its own single velocity after impact. Now, having considered the definition of momentum and impulse, showing how impulse is equal to the change in momentum, and we discuss system of two colliding bodies, showing out the diagrams with the formula. We have the first one, equation, the second equation, and the third equation. These are the basic things you need to know for linear momentum and impulse for any examination. From here, which is the second topic on the book of conservatives, we move over to the third one, which is thermal energy.